I have a past in herding cats, so this comes natural to me. I care about kinds of problems in which everything falls apart. That's called chaos. And my original motivation working on this was to understand quantum field theory when it's strongly coupled. What I'll tell you today is a very elementary contribution to that subject, which I find very pretty, deadly cute. There is something called chaotic field theory, and it's a fashion in the last year or two because several people have written papers on this. And we don't understand each other, and they certainly don't understand me. I'm hoping that what I have to say is of some use. And I'll do it in the following Faust. I'll do it 3 times. First, I'll give you a brief course on chaos in 15 minutes. And then I will do this. Now, I'll do this for a coin flip or a one-dimensional map. So that's not physics. So I'll have to do it as physics. And the physics is mechanical things like springs and rotors. I do it on a rotor. That's called spatiotemporal cat. This is segues in the theory of space-time called spatiotemporal. So the motivation from this comes from many fields, but in very concretely and very easy to understand, but very hard to execute in practices, developing a theory of turbulent fluids or spatiotemporally chaotic fluids. Over the last 20 years, there's been great advance in this field, known to only few, but it's really amazing. And here is a picture of simulation of pipe flow, and these little colors are measuring so-called isovorticity surfaces, you know, how rotational motion of the fluid. You don't have to do this, understand this in detail. But basic thing you learn about turbulence that when you actually look at it and don't just plot a plot for Fisher of lattice that looks like a Gaussian, it has lots of structure, and your task is to describe the structure. There's some kind of vortices of certain size. And one natural question you would like to ask yourself, you know, if I understood a small part of the flow, so one of these little blocks here, could I put these things together like building blocks of turbulence and develop a theory of turbulence in such a way? So that's one way to think about today's talk. If I could do it, what would it look like? Now, I will go into very simple discrete mathematics very soon. You know, there'll be mostly integers around, but this is the motivation. It's really partial differential equations, but I will substitute them by discretization, which is called difference equations. And, you know, it doesn't look like that, but that's what it's supposed to be. So can you build a theory of turbulence, or if you are very sensitive about the word turbulence, chaotic field theory, from little blocks, and do it like we do everything in physics. Use the invariances of the theory. In particular, you want your theory to be as good today in the morning, afternoon, or a year from now. So you want time invariance. And you want it to be equally good in Nottingham, Saint-Jean, or in Atlanta. So you need space invariance. The take-home is this. The way we traditionally think about field theories, we say there are lots of harmonic degrees of freedom. So vacuum is lots of oscillations. And then there's some weak interactions between them. These weak interactions are called, Feynman diagrams in perturbation theory. But basically, thing is like a spring mattress. Chaotic field theory is like that, except instead of being a spring, when you push on this bed, it's actually a bunch of cats, and every cat runs away, but it's confined. You cannot explode your vacuum, so they have to come back. And that turns out to be called a Klein-Gordon equation as opposed to, Helmholtz equation. So that's the basic take-home of what chaotic field theory is supposed to look like. It's a theory where everything is unstable and, a perturbation grows exponentially rather than pushes back by Hooke's law. Or in a very, very elementary way, when you look at stability of anything, then in mechanical systems, there are two kinds of stability of anything. One is oscillatory. So you push and you get motion on ellipses or circles. So these are oscillatory eigenmodes. And chaotic field theory, instead of that, has hyperbolic instability. The basic idea is at this level. And now I'll use this to construct field theory. So I'll do it like Faust says, du musst es dreimal sagen. First time, I'll do very elementary thing.